All right. So octahedral mein, for octahedral complexes, okay. So this is what we've come to, right? So the ones along the axis, which is dx square y square and dz square, is of higher energy, and dxy, dyz, and dxz is of lower energy. So these three set of, again, so the like all 5d orbitals are not degenerate, but these three are of equal energy, these three are degenerate, and these two are again like degenerate, equal energy. Okay. So this set of orbitals dxy, yz, xz, they are called T2g orbitals. So this set is given the name T2g. And this set of these two orbitals are given the name Eg. Okay. So this is only for reference. Like we won't be referring to we won't be referring to individual orbitals. We won't be talking about x, y, y, z, xz. We'll directly just say T2d orbitals or Eg orbitals. T2g means dxy, yz, xz, like these three. And Eg refers to x square, y square, and z square. So just to refresh, Eg orbitals are along the axis. So if this is x-axis, this is y-axis, this is what it looks like. Dz square is along the z-axis. It can be x or y, with a tire in between. That's kind of what it looks like. And T2g orbitals are in between the axis. So if we're talking about dxy, it's between x and y axis. dyz is between y and z axis. Xz is in between x and z axis.
Maybe asked to draw these. Maybe asked to draw these like dx square, y square, dx.
No, like it won't be a straightforward question, but like have it for your, I mean, this is something you're supposed to know right from the beginning of grade 11, the shape of orbitals and all. So, but it's good to know this understanding, because like why do these have higher energy? Because the anions, the ligands are directly approaching them where they are located. They end up with higher energy and these end up with lower energy.
What does EG and T2G stand for?
That's I don't remember right now, but it's something. There are some German words that they're derived from, similar to how you had what EZ like for systrons, something like that. I forgot those German words, but yeah.
Is there a reason for the G and the 2G in the like subscript area?
It stands for a thing, I forgot the full form of it. Now you just refer to them as T2G and these are EG.
Ma'am,
Hmm?
in the graph, I know you may not have it now, but in the first case was no field, and what was the second one?
Spherical field. So it was spherical, it was like all around equal on all sides. So all the orbitals were facing equal amount of energy because it was approaching from all directions.
And the last one?
And this is for octahedral. So it's approaching only from specific points, like where the octahedral ligands are there.
Miss, what did you say the reasoning for EG having more energy as the ligands can?
Can they? Because the ligands are approaching directly on the axis where these orbitals are located. Along the axis. Okay. So, I talk like this process, this splitting. So, formal definition for crystal field splitting. So, splitting of d orbitals due to the presence of ligands in definite geometry. This is called crystal field splitting. So just summarizing whatever we studied. So splitting is happening in the d orbitals. Why or how is it happening? Because ligands are approaching in very specific points. So splitting of d orbitals due to the presence of ligands in definite geometry is called crystal field splitting. Okay. So this difference in energy, so this is denoted by delta naught. And so remember, like if there was a spherical this thing, it would have had certain amount of energy, and then but because it's not spherical, you're saying okay, in some cases it's increasing and some cases it's decreasing. So by how much is this increasing? So this takes up 3/5 delta naught. And by how much is this decreasing? This takes up 2/5 delta naught. Again, very symmetrical. So it's splitting in a ratio of 3:2. So this takes up 3/5 delta naught. So 3/5 delta naught into 2 is equal to 2/5 delta naught into 3. By how much is this decreasing? Is 2/5 of delta naught. The overall difference in energy is termed by delta
Ma'am,
naught.
I looked it up. T means triply degenerate level orbitals, and G is German for like even, like they have the same.
I remember it was some German word is there. Yeah. So triply, acha, because there's three of them, triply degenerate orbitals. Why is there the two? Like did they mention that?
Ma'am, what is delta naught?
Delta naught is the amount, like the difference between like all of these are splitting based on energies, right? So difference in energy between the T2G and EG orbitals. So I think this is called splitting energy. Yeah, you have splitting energy, pairing energy. This should be splitting energy. And why is EG called? What does E stand for?
Some Latin. I don't know.
Grade, like German for even. So same equal energy, same symmetry, perspective inversion center. Exempli crash, yeah. Huh?
Oh, I couldn't find why it's called 2G though.
No, the EG Latin they're talking about is like example, you shorten it to EG, right? That's what they're referring to. Note it down. Let me know when you guys are done. In the meantime, I'm just looking this up. I found a source responded by a chemist. If you guys are interested, I can switch to this screen. They still noting down or finished?
Done.
Okay. So this is splitting energy. This is important. This will come into picture again. So just keep it aside. Okay. So now we know the basics of, okay, there is some sort of splitting happening. Like before, we can't have all 5d orbitals to be equal. It depends on, when a ligand approaches, if the split happens. Again, if you remember how electrons are filled, you always fill electrons in the orbitals with lower energy first, and then you go to higher energy, right? So isliye, that's why you have that whole deal of 1s2, 2s2, 2p6. That is the reason why 4s is being filled first, uske baad 3d gets filled, right? Now, in this situation also, after the split has happened, the electrons will again get filled in the lower energy orbitals, which means it fills up the T2g orbitals first and then goes into the EG orbitals. So, this will lead to, like, this will ultimately decide how many paired or unpaired electrons that particular metal atom is going to have, which in turn affects how many vacant orbitals you have, the magnetic properties, the color, and everything else. So this is how the crystal field theory explains it. Now, another thing is this, like, there is this, we are calling this splitting energy. So any and every negative charge, or any ligand that approaches will not be capable of splitting the d orbitals. So different ligands will have different effects. Some will have stronger charges, some will have weaker charges. So depending on depending on the strength of the ligand, you have something called spectrochemical series. Lots of series. You have reactivity series. when we do electrochemistry, you have electrochemical series, which is based on oxidizing and reducing strength of the metals. This is specific to ligands, and it completely, like, this depends on the strength of the ligands. So you arrange all the ligands according to their strength, and then you get the spectrochemical series. Okay.
Ma'am,
Huh?
splitting of d orbitals means like energy wise, right?
Yeah. So this splitting is happening because the anion is approaching along the axis in between, like in a specific direction. Now, if this anion was like pretty weak, if like it may be weak enough that it won't trigger the splitting also. So that's why we have these spectrochemical series. So only the strong anions will trigger the splitting. The weaker ones will not. In that case, you will follow the regular electronic configuration to figure out hybridization and all. Anyway, so that we'll get into it when we get to it. So spectrochemical series, the series, like the strength of the ligand will also decide how much is this extent of splitting. कभी कभी ऐसा भी हो सकता है कि there's not much of a difference. Might as well be pretty much the same thing only. So sometimes the split is like extremely large. So that's what I mean by strength of the ligand, and that will decide like how much is the splitting between the d orbitals. Okay. So the spectrochemical series, this is the series. This is important. You guys need to know, at least know roughly which one falls on the strong side and which one falls on the weak side of it. Okay. So iodide, the least, followed by bromide, followed by thiocyanate, followed by chloride, followed by sulfide, and then you have fluoride somewhere in the middle. We have hydroxide. Then, so this is oxalate, C2O4 minus. Then you have water. You have NCS minus. So both are thiocyanate, but which atom is being linked to the metal is different in both these cases. In this case, nitrogen links, in this case, sulfur links. Then you have EDTA. So note this with small letters only because this is abbreviation. This is ethylene diamine tetraacetate. It's an organic molecule. Then you have NH3.
What is the short like abbreviation?
This one is,
EDTA.
I'll write it clearly. Then you have,
What is it an abbreviation for?
I'll give you guys like EN and EDTA. I'll just finish the series and I'll write it here. Minus and not. Okay. So the abbreviations, EDTA is ethylene diamine.
Double M.
No. So ammonia ka amine is double N, AMMINE. This is diamine, right? This is the amine group, the NH2 group that we have. See,
Okay.
organic. Tetra acetate.
Also, ma'am, our teacher told we have to write chlorido, bromido,
Actually, I
cyanido.
follow that. ठीक है.
Yeah.
And EN is ethylene diamine. So this is an organic molecule. You have CH2, CH2. NH2, NH2. This one structure is ethylene diamine. So you have two carbons, CH2, CH2, diamine, and tetraacetate, COO minus, COO minus, COO minus, COO minus. Yeah, EDTA is this molecule. That's why it's EDTA4 minus. Ethylene diamine is this molecule. The lone pair on nitrogen is the one that takes part in bonding. In this, it's the lone pair on nitrogen and also the 4 carboxylate ion, all of them get into bonding. Okay. Why do we need the spectrochemical series? So the strong end of the series, like beyond water, if you have ammonia, if you have cyanide, if you have carbonyl, these molecules, you can be pretty sure that OR pairing is going to take place. The splitting is going to take place, which means electrons are going to be paired first. The lower end of the series, you have chloride, bromide, like these sort of ions. Then, yeah, splitting may not take place. Like, see what else is given information. Okay. Why do we need to care about like whether it's being split or not? So this brings us to the next part. How does the electronic configuration work? Okay, let me know once you've finished noting down the series, then I'll go to the next page.
What is spectrochemical series?
This whole
As
series.
in, no, like that I understood. Like electrochemical is how fast, as in a solvent concept, which will replace what, like that, right? For this,
Yeah.
for displacement reaction, that we use that.
This is strength of the ligand. How strong is the field created by the specific ligand? Like when iodide is approaching the metal atom, how strong of a negative field is it creating?
So as in, if you have a solution with I and like if you have basically I and say NH3, then since I is a stronger ligand, it will go and attack the metal and not NH3. Like basically like preference.
No, this is lower. Yeah. So this can get.
Oh yeah. Oh okay. It's lower. So then CO is most.
Yeah.
Yeah. Okay.
Is most. Yeah. This is most. This is least. So these are all like strong ligands. These are weak ligands. Okay. Sia, Kaveri done?
Yes.
1 second. Done.
All right. Now, how is the electronic configuration? Okay. So obviously, like here, we're going to talk about the d block electronic configuration. So when you look at it, up to argon ka configuration. So one is argon is AR. 1s2, 2s2, 2p6, 3s2, 3p6 tak, they are not taking part in bonding at all. Then usually if it's a metal ion, which in most of the cases it is, the 4s2 electrons are lost. And depending on the oxidation state, agar +3 hai, to 1d electron is lost. So here we are only talking about d orbital mein how are the electrons being filled. So electronic configuration specific to d orbitals when splitting is taking place. Okay. So there are 5 of 3d orbitals. So let's say these are T2g orbitals, which is dxy, dyz, dxz. Since they're of equal energy, same symmetry, we can't figure out which is what. It's like px, py, pz. And then next two are eg orbitals. Okay. Suppose you have a configuration of d1 or d2 or d3 up to 3 electrons. In this case, obviously, single electron starts filling up. The T2g orbitals are filled. Okay. This one, whether there is splitting or no splitting doesn't matter because it's always the first T2g orbitals being filled, one each. No difference. Next, electron number 4. When you have the next electron, D4, where does this electron go? So here the splitting matters. So this depends on 2 things. One is delta naught, which is the splitting energy. And there is something called pairing energy. Pairing energy denoted by P. Okay. So pairing energy is basically the energy required in order to pair the electrons. Like obviously, if an electron is already in a particular orbital, if you want to add a second electron, there's going to be interactions between both of these. So there is some pairing energy involved. So if the splitting energy is less than pairing energy, delta naught is less than pairing energy, means it takes more energy to pair the electron than it takes to, the difference between the orbitals is much lesser than how much energy it takes to pair the electron. Making sense? So you have 2 types of energy. One is delta naught, which is the difference in energy between T2g and Eg. And you have pairing energy, which is the energy required to pair the electron. So you have already 3 electrons filled.
Is this only specific for d orbitals? Like, sirf d orbital mein there is delta naught and pairing energy.
Pairing energy usually exists, but usually it's not very consequential. Here, in this case, because, we are
Consequential to what?
Here we are studying about coordinate compounds which involve d orbitals mainly in the bonding, which is why we are studying about it in this context. This we have observed. So this we have observed it in d orbitals because of the formation of coordinate compounds. With S and P orbitals, it is much easier for those electrons to just be lost, form cations and form salts. So we don't come across this sort of a situation there. And P orbitals, again, non-metals, it's easier to just they are not, if they're surrounded by cations, they are anions themselves, right? They won't be surrounded by anions because already the shell is occupied with, like, they have almost like 7 electrons. In order to achieve octet, they just need to gain 1 or 2 electrons. They attract cations rather than anions. So we don't really come across this sort of a situation a lot in p orbitals also. So we mainly come across this sort of a situation in d block elements, which is why coordinate